Hi, my name is Camilo Pino, and today I'm presenting my final project for quantum computer programming, named Experimental Exploration of Virtual Quantum Subspace Expansion using QuizKit. Virtual Quantum Subspace Expansion is a molecular structure simulation technique in which you divide your molecular orbitals into core orbitals, which you assume do not change that much, and thus you do not simulate active orbitals, which you simulate using a quantum computer, and virtual orbitals that you do not simulate but which you use in order to correct the result of the active simulation using just classical calculations. Virtual quantum subspace expansion is based on quantum subspace expansion and variational quantum eigensolver. The idea of these techniques is to exploit the second quantized approach for the Hamiltonian of a molecular electronic structure. In the second quantized approach, you have fermionic creation and annihilation operators for different spin orbitals, and you have multiplied by an integral calculated beforehand. You have linear terms and you have quadratic terms of these operators. This Hamiltonian can be mapped into Pauli operators in order to be measured on a quantum computer using the Jordan-Wigner transform that we see depicted on the three equations below. The idea behind variational quantum eigensolver is to use this optimization problem based on the Rayleigh quotient to obtain an eigenvalue which minimizes the energy of the Hamiltonian for a given ground state. The idea is that using a classical computer, you optimize the parameters of this projection of the Hamiltonian on parameterized ansatz, which is measured on the quantum computer repeated times. You assume for all these three techniques we are talking about that you can prepare a wave function, which is this parameterized ansatz in the active space that represents your guess of the ground state. In quantum subspace expansion, apart from first performing the variational quantum eigensolver and obtaining a ground state, you also defined an additional set of operators called expansion operators. These operators are combinations of creation and annihilation operators for those orbitals in the active space. You can then use these operators to define another approximation for the Hamiltonian called the unrestricted Hamiltonian, which consists of these expansion operators applied to your Hamiltonian and projected onto your best ground state. Since this is definite positive, you can't use overlap matrix with just the expansion operators on the ground state in order to solve the generalized eigenvalue problem and thus obtain a better approximation for the eigenvalue, which is the energy of your ground state, using just additional classical resources without performing additional quantum computations. In virtual quantum subspace expansion, you do not only take into account the active orbitals, you also take into account the virtual orbital, and thus you define these additional expansion operators in this way, the linear and the quadratic, in linear and quadratic forms. Then, analogously to quantum subspace expansion, you calculate an unrestricted Hamiltonian, and you also have overlap matrix in order to be able to solve the generalized eigenvalue problem and obtain a better approximation. We performed some experiments by implementing these techniques using a quantum simulator. We studied the H2, Li2, IH molecules, which are small molecules with known parameters to be simulated using virtual quantum subspace expansion and a variational quantum eigensolver. We defined a minimum distance between the electrons and a maximum distance between the electrons with this step size in order to approximate the corresponding energy. For the H2 molecule, with virtual quantum subspace expansion, we obtain a better approximation. Here we can see the Hartree energy, which is approximated by converting the electronic structure n-body problem into two-body problems. The exact value calculated using a classical eigensolver and using variational quantum subspace expansion. We can see that we obtain lower energies that are more into accord with the reality. This simulation was performed using 0 core orbitals, just two active orbitals, and 8 virtual orbitals. That simulation gave us this really impressive result. For the Li2 ground state energy, in which we used 2 core orbitals, we obtained and finally for the LH ground state energy, we also obtained we also performed experiments with Li2, but the addition of core orbitals confused our results as well as with the LiH molecule. These are our references. Thank you.